In this section, we will discuss electron domain geometry as well as molecular geometry or molecular shape for 5 and 6 electron pairs or 5 and 6 electron domains on the central atom. In addition, we will talk about bond polarity and polarity of the whole molecule. Let me begin with trigonal bipyramidal domain geometry. And let me show you that how it would look like. You have a triangular base. So this is the central atom. And one pair on the top, one pair on the bottom. So let me show you with electron pairs without any bonded atom. So central atom, when you have 5 pairs of electrons, it would look like this. Trigonal planar, one pair on the top of it, perpendicular to it, and the other pair is in the bottom of that. When all these 5 pairs get bonded, then molecular shape would be same as electron pair shape or geometry. So that's why PCl5 would have this geometry, which would have the name of this geometry is trigonal bipyramidal. Now it could be that all of these electron pairs get bonded, or some of these get bonded. Based on that, you have different shapes like seesaw for SF4, and then you have T-shaped, and also you have linear for XCF2. Now the question is, out of a number of possibilities, how do we know that T-shaped would be the most stable geometry when there are three groups bonded, or 3 atoms bonded to the central atom, and 2 pairs remain unbonded? We are going to explain that in next couple of slides, so that if you don't want to memorize, then try to understand what I'm going to discuss next. Predicting the best shape when more than one shape is possible. Now, stability of molecular shape is determined by following destabilizing interactions. So when there are 2 such electron pairs, we call it unshared electron pair or lone pairs, the 90-degree lone pair interaction is highly destabilizing. So that's the worst kind that one can expect in a molecule, followed by 90-degree lone pair bond pair. Remember the lone pair? Lone pair means pair of electrons sitting on an atom. Bond pair means is bonded with another atom. I'll give an example, but right now let me establish this destabilizing interactions. So 90-degree would be the worst kind of interaction, and the best kind would be 90-degree bond pair interaction. So we'll go over a specific example. Now let me go over ClF3 and explain to you, out of a number of possible shapes, how we can get the best shape. That way you don't need to memorize. Now first you need to write down the valence electrons on each atom, Cl. You know that is, if you count from left to the right until you get Cl, so pretty much S and P electrons, that would be 7 valence electrons. Each fluorine would have 7. Now you have 3 such fluorine in ClF3. That's 21 electrons. So altogether we must account for 28 electrons. Now let's write down the central atom. Central atom is the one that's present in least number. So Cl at the center. And let's have 3 fluorine bonded, F3, and give noble gas configuration to outer atoms or fluorine. So 2, 4, 6. 2, 4, 6, because it already has 1 pair, so that makes it total 8 electrons. So now I have assigned all 8 electrons around the outer atoms. 3 such outer atoms would have then 24. Then I have 4 more electrons. So 1 pair here, and those extra pairs has to go to the central atom. So now central atom, Cl, has 5 electron pairs. So Cl has 5 electron pair. And 5 electron pair would give you trigonal bipyramidal shape. So let me write down that. So electron domain geometry would be trigonal bipyramidal. So this is trigonal. I have Cl here, 3, 4, 5. So that's one of them. And you need to place 3F. And there are 3 possible structures or geometries that I can have. So let me write down first one. But you would have here one F, second F, third F. And then these are electron pairs. Remember, there are total 5 pairs. So we'll call it structure number 1. And let me draw structure number 2 now. So structure number 2, again, you'd have a trigonal planar structure. So this is trigonal planar, Cl. That's making the plane. And then on the top, on the bottom, and I have electron pair, and then fluorine are all on the triangular plane. And in triangular plane, since it's triangular, angles will be 120 degrees from each other. So that's structure number 2. There is another structure possible. Again, let's draw that. Again, Cl at the center. And one on the top, another on the bottom, on the pair. Now let's now choose, this goes to the top, fluorine here, and then electron pair here, second fluorine here on that triangular plane, and third fluorine is also on the triangular plane, and rest would be all electron pairs. So this is structure number 3. Remember, we say that 90-degree lone pair interaction is most deactivating. So whenever you discover that in any possible structure, you just get rid of that. In this case, structure number 3, you can see that this electron pair and the other electron pair is at 90 degrees from each other. And that interaction will be most, this interaction is most destabilizing. So in other words, you're going to ignore this structure, since nature always favors the stable structure. Now focus only on 1 and 2. And none of these have 90-degree lone pair interaction. The structure number 1, you might think that this is 90 degrees, but truly this is a 120-degree angle. So we don't need to worry about that 90 degrees. So there is no 90-degree lone pair interaction in 1 or 2. So let's focus on now 90-degree lone pair bond pair. We can write down 0, 90 degree. Let me write down here in each case 1 and 2, the 0 degree, 0, 90 degree lone pair. That's the case for each of these. So none of them have 90 degree lone pair. And now focus on lone pair bond pair. Let's write down separately. In case of structure 1, we would have 1, 2, 3. You can see here, I can see 2 for this fluorine interacting with electron pair on the triangular base. So there'll be 2 such interactions for the top fluorine, and for bottom fluorine also 2 such interactions. So altogether there'll be 4. So 4 90-degree lone pair bond pair. Let me identify you. This is the bond, one of those lone pair bond pair. This is the lone pair, and that's the bond pair. And that can happen on the top as well as for the bottom fluorine. So that makes altogether 4. Now There are two 90-degree bond pair. You can see bond pair, this is the two fluorine. Okay, let me draw a square around those fluorine. This is one fluorine, this is the other fluorine. That's 90 degree. So that's two 90-degree bond pair. Now let's look at structure number 2. In structure number 2, we have, just like structure 1, there's no 90-degree lone pair interaction, but there are 6 lone pair bond pair interactions, 6 90-degree lone pair bond pair interaction, and there is no 90-degree bond pair interaction. Now between lone pair bond pair and bond pair, it's a lone pair is the most destabilizing, more destabilizing than the other one. So number 2 is less stable than number 1, and since nature favors the most stable one, so 1 is the best structure, and that's called T-shaped, because if you take the picture of the molecule, you're not going to see those electron pairs. So cover the electron pairs and it looks like this. And that's T-shaped. So now you have two options when you study this section. You can either memorize or go by this lone pair, bond pair, and bond pair interactions. Again, here we are showing some of these interactions. As you can see, with 4 bonded pairs, and in case of octahedral electron domain, this is octahedral. Octahedral means, let me draw a bigger picture of it so that you understand it. Here you would have it base like this. You have a central atom here. 1, 2, 3, 4, 5, 6. So these all have electron pairs, and that makes it octahedral, and angles are all 90 degree. So that's octahedral. When all of them are bonded, like in SF6, molecular shape would be same as electron domain shape, or octahedral. On the other hand, only 5 are bonded, then you get what is called a square pyramidal. Only 4 are bonded, you get a square planar. XCF4 is a good example of that. Again, in each case, you'll be able to predict the right geometry on the basis of lone pair, bond pair, and bond pair interactions at 90 degree. For larger molecules, there are lots of central atoms. So in other words, when you talk about shape, you need to talk about shape around each of these central atoms. So there wouldn't be one unique geometry. You would have more than one geometry around each central atom. By central atom, I mean atom which is bonded to more than one atom. Now we are going to talk about polar bond and polarity of molecule. How do I determine a polar bond? If there is an electronegativity difference between two bonded atoms, then that bond is going to be a polar bond. Let me show you a simple example of that. Say I'm looking at carbon-chlorine bond. Chlorine is more electronegative than carbon, so it's going to pull electron away from carbon. So there'll be a direction. This arrow indicates the direction in which electron would be moving from the center towards Cl, because Cl is more electronegative. Normally, elements on the right side of periodic table would be more electronegative than elements on the left hand side, except the noble gases. So there are a couple of things we need to know before I know whether a whole molecule is going to be polar or not. First, we need to look at whether each bond is polar. by looking at electronegativity difference. Then write down the shape of the molecule and add up all those dipole forces. If there is no resulting force, that means it's a nonpolar molecule. We'll give you examples. Carbon dioxide, for example. Let me draw carbon dioxide, carbon with 2 double bonds. Now, of course, there are now 2 electron domains, one on each side of carbon, and that gives a linear geometry for carbon dioxide. So let's just write down carbon dioxide like this. Each carbon-oxygen bond is a polar bond because oxygen is more electronegative. It's on the right-hand side of carbon in periodic table. So it's more electronegative. Since it's more electronegative, it's going to pull electron away from carbon. That's the force. That's called dipole moment. And there'll be another force just on the opposite direction. Since the shape is linear, angle is 180 degrees, so it's 180 degrees. Will there be a net force? Answer is no. Think about, you are pushing a table from one side to the other side, and there is another gentleman who is pushing it from the other end. So this is the table. So this location of the carbon is the location of the table. Think it this way. Say you are pushing it this way along the line, and another gentleman is pushing it this way, and both of you are pushing at the same, with same kind of energy or force. So there'll be no net effect. The table is not going to move. Equal and opposite, and they're going to cancel out. And that's the case for a non-polar molecule. Even though each bond is a polar, but net effect is non-polar. It's like saying that each of you are pushing the table, but there is no net effect on the table because 2 of these forces are canceling out. On the other hand, if it's not a linear molecule, for example H2O, it's a bent molecule. Oxygen, and let's write down hydrogens. It's a bent molecule. Again, oxygen is more electronegative than hydrogen, so dipole is always from positive towards negative. And hydrogen, so it's always pulled towards more electronegative element. So there is a net force because it is acting at an angle. Now think about, let me highlight this molecule. Say your table is sitting there and you are pushing this table along this direction and another person is pushing it along this direction. Both of you are equally strong. This time it's not equal and opposite because it's an angle. What do you think? Do you think that table is going to move? Answer is yes. They don't cancel out. The net effect is going to be somewhere in the middle. So the table is going to move along this direction. Same is the case with bond polarity. Here the bond polarities, dipole moments don't cancel out since they're acting at an angle less than 180 degrees. So that's why there's a net effect which is shown by this arrow. So H2O is a polar molecule, and because of the polarity it's a strongly bonded liquid. On the other hand, carbon dioxide is a nonpolar molecule. It's a gas at room temperature. Now here you're seeing other molecules. Carbon tetrachloride. Here we are seeing all these forces. These end atoms are Cl. The central one is carbon. Since Cl is more electronegative, so arrowhead is towards Cl. Now they all cancel out. It may not seem that obvious to you unless you make a model. Now keep something in mind. For a highly symmetrical structure like linear, tetrahedral, trigonal, planar, if I have the same atom bonded, all of their dipole forces cancel out and they become nonpolar molecule. But whenever there is a broken symmetry, then it's going to be polar. Like in case of ammonia, there's a broken symmetry because the fourth object is missing. So these 3 forces acting on between hydrogen and nitrogen, they don't cancel out. So keep that in mind. And also, you may have a tetrahedral, but you may have a different atoms. Like in this case, the bottom case, CH3Cl, there is a Cl. So that's 3 hydrogen, hydrogen, hydrogen. Carbon and hydrogen are almost the same electronegativity, so we can ignore their bond polarity. That's a tiny bit, almost we can ignore that. So mainly bond polarity is due to CCl bond, which is shown with this arrow. So when you determine whether a whole molecule is going to be polar or not, you'll have to take into account all these cases, which atoms are bonded, whether there is an electronegativity difference or not, what's the shape of the whole molecule, and then add up all the forces. For a highly symmetrical shape, they would all cancel out. Again, remind you, highly symmetrical means linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and they're all bonded to the same atom. They would all cancel out.